B12, the binomial expansion for non-whole numbers. Let's review the binomial expansion. You have a plus b to the nth power, where n is a whole number, 0, 1, 2, 3, 4, 5, etc. And this is the sum where k goes from 0 to n of n factorial over here k factorial n minus k factorial. Then we have a to the n minus k and b to the k. Now we have already derived this formula, and this part in here appears often in mathematics, and that's defined to be n with a k here and these two parentheses. Now I'm going to show you a memory trick. If we have a plus b to the nth power, and I'm going to write this here just so that you can see this notation, because a lot of times you see this written like this, and then you have a to the n minus k and b to the k. Now here's the trick. In practice, I refer to this formula when I work this out. So if I go a plus b to the nth power, where say k is equal to 0, it's easier for me right now to refer to this top one. Then I would have n factorial over k is 0, 0 factorial, and then n minus k is n factorial, like that. And that would be a to the nth power, because k is 0, n minus 0 is n, and b here to the k power would be the 0th power. Now the next term would be n factorial, where k is equal to 1, n factorial over 1 factorial, and then n minus 1 factorial, just applying this formula. Then we would have a to the n minus 1, and we would have b to the first power. Notice that n factorial is always on top, so I can write down here for the next term n factorial again. And then now k is 2. This is 2 factorial, and then we have n minus 2 factorial. And then for the a, we have n minus k. K is 2 now, so that would be n minus 2. And then for the b to the k would be just 2. All right. So this first one here is k equal to 0. This next one is k equal to 1. And this one is k equal to 2. Now we can do one more. Let's put one more in here. Plus n factorial over 3 factorial. So we have 1, 2, now we have 3. And then we have n minus 3. Just like we had n minus 1, n minus 2, n minus 3. We'll have a to the n minus 3, and we'll have b to the third power. And then dot, 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 like that. So this one here is the k equal 3 term. All right, now, here's what we're going to do. I'm going to write this out again. A plus b to the nth power. But for this first one, I'm going to notice that the n factorial over n factorial, they cancel out. So we just have a 1 here. And this is a to the nth power, b is 0. Now this next term, notice that the n factorial divided by n minus 1 factorial is going to leave you just the n by itself. Because the n factorial is n times n minus 1, dot, 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 dot. So I can replace the n factorial with n times the quantity n minus 1 factorial, which will cancel. 1 factorial down here is just 1. So I have this formula, and this will be n minus 1 and b to the first power. Then for the next term, we'll have n factorial divided by n minus 2 factorial. You're just going to have n times n minus 1. Because the next term, n minus 2, and then et cetera, will cancel the n minus 2 factorial there. And here I'm going to have just 2. I'm going to put down 1 times 2 like that. And this is a to the n minus 2, b to the 2. And now for the next term, if I have n factorial over the quantity n minus 3 factorial, there's a factorial there that I had left out earlier. And let's fix that. Then we're going to have n times n minus 1 times n minus 2. And then we're going to divide by 3 factorial. I'm going to put down 1 times 2 times 3. And then that'll be it. That's what we have. And this is a to the n minus 3 and k to the b and b to the third power. All right, now, so you can figure out the next one by a rule that's emerging. You have, for the fourth case, you have n minus 1, n minus 2, n minus 3. I count backwards four factors here. And then I divide by counting forward with 4 factors. And that's the rule. And this is n minus 4, and this is b to the 4th power. All right, so here we're actually going to do the plus sign here, and then we'll do the dot, dot, dot. Okay, now, here's the rule. You simply look at your general term. Say if it's 3, you just count backwards, n minus 1, n minus 2, three things, and you divide by counting forward 3 things. So that's a memory trick that I use. So I'll put down here, memory trick. Then I don't have to try to remember all this stuff up here. I just use this approach. Now I asked my calculus teacher when I was a freshman in college at Philadelphia, St. Joseph's College. It was called at the time, now it's university. I asked if this would apply if n is not just a whole number, like what about other numbers? And he said, yes, it does apply. So I'm going to ask the question, what about 1 plus x with the minus 1? Now you would say here, if I use this formula, I have minus 1 factorials. I don't know what that is, but I do know this prescription. I would use this prescription. I'm going to try it and see if it works. All right. Now, to do this, I just want to show you that it's convenient for me, easier for me to just pull the a out, a to the n out of here. So I have 1 plus b over a to the nth power, and then just call this x. So it's easier to work. It's easier to work with just 1 plus something. And you can see that if it works for here, we can go ahead and adapt it by looking at an a term and go back and make it more complicated. So this is really all I need, since I'm going to pull out that a to the n, and then here I'm going to be looking at just this part here, see? And this part here is going to be 1 plus x to the nth power. Yeah, just a little bit easier to show things. Well, what about this? Now, it turns out I can actually work this out by long division. Now, I learned long division in grade school. If you don't know about long division here, you may not, if you being younger, I'm going to show you how to do a long division problem. Say I want to divide 4 into 25. I would say, how many times does 4 go into 2? And it doesn't go in at all, 0. And then 0 times 4 is 0. And then I would subtract 0 from 2 and bring the 2 down. And then I would bring the 5 down. How many times does 4 go into 25? Well, 6 times 4 is 24. Doesn't quite do it, so if I subtract here, I bring a 1 down, and now here's where I would put the decimal point in a 0 because I need to have something else here. So then I would bring the 0 down. How many times does 4 go into 10? Notice I don't worry about a decimal point down here, but I do put it here. 4 goes into 10 2 times. 2 times 4 is 8, so there's more, not just 2 exactly, but that's okay. We get the closest thing. Now we subtract and get the 2. Now we need another 0 to come down here. How many times does 4 go into 20? 5 times, and 5 times 4 is 20. And now when we subtract and get 0, we're finished. Now that's a leading 0 we don't need to worry about. This is equal to 6.25. 6 1/4. All right, that's long division. So I'm going to use long division to figure out what this is. 1 over 1 plus x, because that's what that minus sign means. So here, to do this problem, we're going to have 1 plus x, long division, go into 1. Well, how many times does 1 plus x go into 1? Well, here, the closest thing, I want to get rid of that 1, so I put a 1 here and 1 plus x. See, then when I subtract, I can get rid of that 1, but then I pay a price. I wind up with something else. Because remember our prescription, when you multiply this number by this one, we then need to subtract, and we got rid of that 1, which is my intent, but now I got to get rid of this. So here, a minus x will do that. So minus x times 1 is a minus x, but I'm getting something extra here. When I multiply these together, I get a minus x squared. So now when I do my long division subtraction, I did get rid of this first thing. I got a 0 there, but now when I subtract here, I got a plus x squared to deal with. Well, I'm going to multiply that 1 by the plus x squared so I can get rid of it. So multiply these together, you get x squared, but then you get this extra cube term. And then when you subtract, you get the 0 minus x cubed. Well, to get rid of the x cubed, I would need here a minus x cubed. So when I multiply here, I get minus x cubed minus x to the 4th. And then when I subtract, I get x to the 4th. And you can see what's happening here. We're going to have alternating signs, and these powers are going to be increasing, and we're going to keep going. We're going to keep going. So my question is, does my prescription here get this? All right. So we're going to try it out. All right. So here, if we look at this, we're going to have 1 plus x to the minus 1, and that's going to be equal to, well, first thing I do is I put a 1 down, and then the a to the nth power, a to the negative 1 power is 1, and x to the 0th power is 1, so that's all I have. Now the second term here would be, I would put the n down over 1. I count just using my prescription, counting backwards with just a 1 factor, so that would mean here I would have a minus x over 1. You see, a is 1, and a to any power is 1, so I'm always going to have a 1 here. I'm just going to focus on the b. The b is the x, and here we're going to have x to, the formula says, to the first power. which is what this is. If I wrote everything out with the formula, I would have here a plus. If I were to write this out exactly, I have a plus, then the n is a -1, and I would then divide by the 1. And then 1 to any power is 1, and b is the x. I would have this. Then using the formula very, very precisely, I would count backwards now here 2 times. There are 2 factors, so I have this. And then I would divide by counting forward like this. And then remember, the a is 1, so to any power, that's going to be 1. I just need to now put the x down squared. And then the next one would be a -1, a -2, and a -3. The backward rule over 1 times 2 times 3, and this is x to the 4th. X to this cube, sorry. All right, then the next one would be -1, -2, -3, -4, but over 1 times 2 times 3 times 4, x to the 4th. I saw that 4 there, got confused. All right, so now if we look at this, we can see we have 1, we have this, and then we have the next term, is that one, and this next term is going to be the x squared, and the 2 minus signs are going to cancel. We're going to have that. The next one, we have an odd number of minus signs, so it'll be negative, but you know, the 1, 2, 3 cancels the 1, 2, 3. We have that. And here we have an even number of minus signs, so it'll be plus, and then the 1, 2, 3, 4 is going to cancel the 1, 2, 3, 4. It looks like it works. Isn't that wild? Okay, now I'm going to ask, what about 1 plus x to the 1/2 power? Now see, that is equal to the square root of 1 plus x. Can this work? Well, using my prescription, we can try. So we have 1 plus x to the 1/2 power. I would start with the 1, and then I would now going to go working backwards on here just 1 time, so that's the 1/2 over the 1 going forward, and then we put the x down, and then we have plus, we have 1/2, and then we're going to count backwards, so that's then subtract 1, and then we stop. See, we don't have to worry about factorials. We're using my prescription here, my memory trick, x squared, and then here we have 1/2. Count backwards, -1/2, one more time, -3/2, and then count forward, 1 times 2 times 3, x to the cubed, and we'll do one more, 1/2, -1/2, -3/2, -5/2, and then we'll go 1, 2, 3, 4, and that's x to the 4th power, ... Okay, so what do we have here? For 1 plus x to the 1/2 power, we have a 1 plus a half x. What's this? This is 1 over 2, 1 over 2, and it's divided by 2, so that's going to be 1 over 8 with the minus sign, and that's x squared. What's the next term? Next term is going to be positive because 2 negatives cancel. And what do we have here? We have 2, 2, 2 in the denominator, another 2, that's a 16. 3's cancel. So we have 1 over 16 x cubed. The next one's going to be a minus overall because there's odd number of minus signs. And we're going to have here the 3 will cancel this 3. But now we have 2 times 2 times 2 times 2 in the denominator, that's 16. And then we're going to have here divided by 2 again. So that's in the denominator, it's going to be 32. And then 4 times 32, well, if you double 32, you get 64, and double again, 128. So this is going to be 5 over 128. times x to the fourth. Now, I'm not going to, prove this rigorously mathematically speaking. I'm going to do this the way a physicist or the engineer would do it. And remember, in physics, we are cavalier like this because the real test for us is not rigorous mathematical proof. It is nature. When we calculate things in physics, it's always checked with nature. So nature is my guide. So I just want to be reasonable here. So by being reasonable, I'm going to put in a weird number for x, 1 over 5, and use my calculator and see if this comes close. So if I use my calculator, I take 1 plus 1 over 5 and take the square root. I get 1.0954. And I encourage you to do this to this many digits. All right, so this is by calculator. Calculator gives this. Now I'm going to use the calculator with my formula. And with my formula, I have here, this first term is 1. But then if I add with the second term, and remember here what I'm going to do, let's go ahead and write this out. This will be 1 plus 1/2 times 1/5. This is what we're interested in. Plus 1/8 times 1 over 25. That's the 1/5 squared. And then plus 1/16 over 1/5 cubed. 5 times 5 is 25, and times 5 again is 125. And then minus 5 over 128. And now what is 1 over 5 to the 4th power? Well, that would be 25 times 25. 25 times 25, for some reason, I remember that, 625. Okay, so now if the first term is 1, that's not too good of an agreement, but if I add this, I get 1 plus 1/10. So I get this. But now if I add the next one, now I did this with a calculator. I have 1 plus 0.9500. And then if I go with the next term, I got 1.0955. And then if I go with the next term, I got 1.0954. Now, for a physicist, we would proceed and do our physics. Because eventually, it's nature that's going to tell us if we're right or wrong. But this, to me, is not a coincidence. Is it a formal mathematical proof? And no, it's not. And we don't do that in physics all the time. Sometimes we do, but not all the time. Most of the time we don't. Okay, so now I'm wondering about 1 plus x to the 1/3 power. That's taking like a cube root. Checking a few here. 1 plus, all right, well, I have 1/3 over 1 to the x. And then here, if we count the backward trick, 1/3, we subtract, we get minus 2/3. Count forward, 1 times 2, x squared. Then we would go 1/3 minus 2/3, all right? And we would have then minus 5/3, subtracting 1. And then here 1 times 2 times 3, x cubed. And then we would have here a fourth term would be 1/3 minus 2/3. Just copy these down again. And then we're going to subtract 1. So it's like subtracting a minus. We're going to be minus 3 over 3. And that's going to get us here. And that would give us here minus 8/3. Subtract another 3 over 3. And that's x to the 4th. And we would divide by 1 times 2 times 3 times 4, like that. So if I come over to here and put in a 1/5 for that x and use the calculator, I get 1.0627. And then if I look at the first term, it's a 1. If I look at the second term, where x, is 1/5, and use the calculator, multiplied by the 1/3, I get 1.0667. If I do this one, I encourage you to do this with your calculator, 1.0622. And then here, 1.0627. I'm thinking, whoa, look at that. Need I go on? I don't think so. I think we're good here. One last one here. What about 1 plus x to the pi power? Like, what is this? And we're really checking out a few cases here where n is not a whole number. And then I want this to be 1/5. So by the calculator, I get 1.773 by the calculator. Well, what about the formula? Well, I'd have a 1 plus pi over 1 times x. Then I would count backwards, see, pi and pi minus 1, and then count forward. That's x squared. Then I would have pi minus 1, pi minus 2. Notice I avoid any factorials here. Isn't that nice? X cubed. And then here, pi minus 1, pi minus 2, pi minus 3. That's 4 of them. And 1 times 2 times 3 times 4, x to the 4th. All right, well, what are we looking at here? We're looking at 1 plus pi times a 5th for our specific case. And then plus here, pi times pi minus 1 over 2 times 1/5 squared. And then plus pi minus 1, pi minus 2 over, I'll just write these out like this. Use a calculator. 1 over 5 cubed. And plus pi minus 1, pi minus 2, pi minus 3 over 1 times 2 times 3 times 4. And this is 1/5 to the 4th power. 1/5 to the 4th power. Okay, this is 1.000. This, with the calculator, is 1.6283. This gets me 1.7629. And this gets me 1.773. I'm just going to stop here because, look at that. Not a coincidence. Well, I hope you found this enjoyable. Extending the formula to non-whole numbers using my memory trick here and avoiding factorials.